Hello everyone, in this tutorial I will show you how to do a quasi-static analysis of a metal forming process. This will consist of applying a displacement boundary condition to a rigid punch against a deformable plate and observing the strain that is developed in the plate as it is deformed. And this will be performed with an explicit dynamic step using mass scaling. So I've already defined the blank and the punch. This is the blank. We have quite a fine mesh. Perhaps doesn't have to be so fine. And for the blank, I'll switch to the mesh module and show you that I'm using currently linear incompatible mode elements. So linear elements, they do not capture bending particularly well unless we stack several layers of linear elements with reduced integration. Alternatively, we can switch to incompatible modes, which will add internal degrees of freedom to the element to improve the bending characteristics. And in this case, we probably don't require so many elements through the thickness. However, just for the sake of illustration, I will keep incompatible modes and I won't make any modifications to this mesh. The other part is the punch. And I've modeled the punch as a discrete rigid, which can be done by selecting create part and then discrete rigid solid revolution. So in the whole model, I'm taking advantage of quarter symmetry, so I only model a quarter of the punch head. The punch is meshed with rigid elements, and in order to do this, since rigid elements only apply to the faces of the component, we have to select shape and then shell from solid. You would select the rigid component. In this case, I can't because I've already converted it to a shell. And then you would select done. The other important thing to remember with the rigid geometry is to create a reference point which will be associated with the part. And this is done by going to Tools, Reference Point. Since the analysis is dynamic, the inertial effects are going to affect the solution. And currently, since this component contains no section properties, it has no mass. So we will have to apply a mass to this component. And the way that I do this is to apply a point mass to the reference point. To do this, we expand the container for the punch part. And under engineering features and inertias, I've created an inertia here. For the region, I picked the reference point and I chose a mass in tons, which corresponds roughly to the equivalent mass of the punch, taking into consideration its volume. Now, since we're only interested in the translational motion, I've left the rotary inertia definitions empty. For the material properties, we require the density and the elastic and plastic properties of the blank component. So using the SI millimeter system, I've specified a density corresponding to approximately 7,800 kilograms per meter cubed, some elastic properties and some plastic properties. Here I used the Ramberg-Osgood nonlinear elastic model to generate some test points with true yield stress versus the logarithmic strain. We need to create a section property for the blank, and this can just be a solid homogeneous section using the material that I created earlier. Then if I switch to the blank and double-click section assignments, I will assign the material to the entire part. Okay, so now we're going to instance the blank and the punch. And to do this, we double-click on instances, we choose the blank, and using the auto offset feature I will instance the punch as well. Before I apply position constraints between the blank and the punch, I'm first going to rotate the blank so that the deformation direction is parallel to the Y direction. Choose the axis of rotation and accept 90 degrees. Now, to move the punch to the correct location, I'm going to use the coincident point constraint, choose the vertex of the punch and the lower vertex of the blank here. And this moves the punch to the blank, and we verify that the symmetry or the position of the punch is correct relative to the blank, which it is. So now that we have the assembly instances, I'm going to create a few sets and surfaces which will aid us in the modeling process later on. So I'll first create a set which I'll name RP, and this will belong to the reference point of the punch. Next, I'll create an element set called blank, and this will contain the elements of just the blank. Next, I'll create a geometry set called fix blank, and this will be used to fix the blank in space using the Incastra constraint. Next, I'll create an element set for the punch, and I'll call this punch. I will create two more sets. I'll create a set to define symmetry in the X direction, and another set to define symmetry in the Z direction. Next, I'll create a couple of surfaces. We're going to have to define contact later on, so we need a master and a slave surface. The master surface must belong to the deformable part, whereas the slave surface belongs to the rigid part. So I'll select just the contacting area of the punch. Make sure that we're using the correct shell face of the punch, which we are, so I will accept that. Before we add the dynamic step, I'm going to define a few boundary conditions which define the state of the model before the analysis step. The first boundary condition I'll create is the Incastra condition for the blank, and I'll select the first boundary condition type. If we go down to sets and highlight in viewport, I can see here the set that we're using for the boundary condition. I'll choose Incastra. The next boundary condition I'll create, I will call fix punch. Now we're going to move the punch vertically upwards into the plate. However, we want to constrain all the degrees of freedom other than the global 2 degree of freedom. And I will apply this boundary condition to the reference point of the punch. The other important reason for suppressing the rotational degrees of freedom is that, if you remember, for the point mass inertia, I left the moments of inertia empty. So it's important that we don't allow any rotation, otherwise the rotation will be zero energy because there will be no inertia and the analysis won't converge. So we suppress all degrees of freedom on the punch except for the global 2 direction. Okay, I'll create a couple more boundary conditions. First, for the X symmetry, choose the appropriate set and select X symmetry. Then once again, I'll choose the Z symmetry and choose Z. Okay, so now we can go ahead and we can define the analysis procedure. So I'll double click on steps and I will select dynamic explicit as the procedure type. NLGeom should definitely be on since we're looking at very large deformation. In the real experiment, this would go on for several minutes. However, in explicit, we can only solve efficiently if we look at smaller time periods. So we're going to have to accelerate the procedure, and I'm going to condense the time down to 2 seconds. Now, there are some important considerations for the time period in an explicit step, especially for quasi-static simulations, that we have to be careful about in order to ensure the accuracy of the solution. But for now, I'll just select a time period of 2 seconds. We will accept default incrementation. And for mass scaling, I'm going to select to use our own definition, and I will create a definition and choose a factor of 1 million. So this will scale the mass in the model by a factor of 1 million. We'll then define the movement of the punch into the plate. Now, in quasi-static simulations, we want to ensure that we don't incur sudden changes in energy, whether it be kinetic or internal energy. So if we simply push the punch into the plate at a constant velocity, then we'll incur a very large, almost step change in energy. So to ramp the displacement, I'm going to create a smooth step, which is a fifth order polynomial curve. So this will ensure that the displacement at the beginning and the end of the step will be smooth. And I will call this smooth step. And I will choose 0, 0, and 2, 1. So we say that we will apply the full displacement of the punch by the time we reach the end of the step, which in our case is 2 seconds. Then I'll create the boundary condition, and this will be applied to step 1, and I will call this move punch. This boundary condition we will apply to the reference point of the punch, and I will select a displacement of 12 millimeters, and I will choose the smooth step amplitude. We then have to define contact between the punch and the blank. I'm going to choose a frictional interaction property, so I'll double click interaction properties, and I will call this one friction 0.2. I will choose a tangential and a normal behavior. For the normal behavior, I will accept the hard contact with the default enforcement method. And for the tangential behavior, I will choose penalty, and I will specify a coefficient of friction of 0.2. Then we create the contact interaction itself by double-clicking on interactions. I will name this contact. And since we only have 2 surfaces in contact, I will choose the surface-to-surface contact interaction. For the master surface, I will choose the surface we created earlier. And you can see it appears that I've created the surface on the wrong side of the blank. So what I will do is go back and reselect the surface on the correct side. Okay, so let's try that again. I will select surfaces, master, and this time we specify the surface on the correct side. Then for the second surface, I will choose again surface and slave. I'm going to switch to the penalty contact method because this will ease the solution later on, and I will stick to the finite sliding since we want to allow an arbitrary amount of sliding between the punch head and the blank. Make sure that the friction property is selected and click OK. Next, we want to create some output requests. So I'm going to delete the default output requests and we'll create some of our own. So first, I'm going to request field output for the blank, and I choose set blank, so we're only writing output for the blank element here. I will select 100 evenly spaced time intervals, and I will choose the stresses and the plastic strain components, equivalent strain, nominal, and logarithmic. I'll create another field output, and this will be for the whole model. So we choose whole model, again 100. I just want to get some smooth animation at the end, basically. And here I will just select the translations and rotations. Okay, next we'll create a couple of history output requests. I will create one for the blank, select set blank, choose 100 evenly spaced intervals, and I'm going to look at the energy total. So I'm going to want to compare the internal energy to the kinetic energy. So when we do quasi-static analyses, we have to make sure that the inertial forces are kept to a minimum. Otherwise, the static nature of the procedure will diverge towards a more dynamic behavior, and that's what we want to avoid. So the easiest way to check this is to compare the kinetic energy to the internal energy and make sure that the kinetic energy is no more than 5% of the internal energy. But it's very important that we select only the blank. If we include the punch as well, then we include the kinetic energy from the rigid body rotation, the rigid body translation of the punch, and this will give us an incorrect picture of what's going on. Okay, so one more history output now. We'll create an output for the punch. And I'm just going to look at the reference point of the punch, again, 100 evenly spaced time intervals. And this time we just want to look at the displacement in the global 2 direction and perhaps as well the velocity. So I'll choose V2 as well. Okay, so that's everything modeled. There's no guarantee here that we'll get the parameters correct the first time, and by this I mean the mass scaling, the duration of the step, and the speed of the load application, or the total displacement that we're applying, because what we want to do is keep the stable time increment as high as possible so that we're not waiting for days for the analysis to complete, but we also want to minimize the kinetic energy. So we applied a mass scaling factor of 1,000,000, and what this does is it will increase the stable time increment, but it will also increase the kinetic energy in the system. So we have to be careful. The larger the mass scaling, the faster the analysis will run, but the more kinetic energy we will incur in the model. Now, as for the load application, we compare the displacement that we're applying with 12 millimeters to the step time of 2 seconds. So the shorter the step time, the shorter the analysis will run for, but the faster the punch is going to cover those 12 millimeters. And the speed of the punch, by just doubling the speed of the punch, we actually will increase the kinetic energy by a factor of 4. So we've got to be very careful to find the correct balance between the load application and the time period and the mass scaling. So let's see how this analysis runs. I'm going to create a job. I will just call it forming tutorial. And here we're going to invoke the double precision solver. So I'll submit this job for analysis, and we can monitor the progress of the solution throughout the step. Once the analysis has completed, we can switch to the visualization module and look at the stress and the strain history in the model. You can see the punch being applied through a 12 millimeter displacement. You can see how much the elements here are deforming and how large the stresses are. If we switch to the logarithmic, the in-plane component in the one direction, we can see that the maximum logarithmic strain in this case is just over 100%. So we're seeing some very large strains here. Now, to verify the result, one thing we can do is check the kinetic energy history with the internal energy. So by expanding the history container, we can see we have our internal and kinetic energy variables. If I highlight both of them and select plot, you can see that the kinetic energy in this case is only a very, very small fraction of the internal energy, less than a 100% in this case. It would be possible to increase the kinetic energy by a factor of about 63,000 in this case. And that would translate to being able to increase the punch velocity, or rather decrease the step time, by a factor of 250. So here we have potentially a very good quality solution because we've been able to keep the response quite static throughout. However, the kinetic energies in this case are so negligible that the analysis was actually quite wasteful, and we probably spent longer analyzing the model than we had to. We can also look at the U2 variable. We can see how the displacement was applied in this smooth step, and this helped to maintain a very low change in energy at the beginning of the analysis and at the end as well. Now, if we differentiate the displacement history, we end up with the velocity history, and the same story applies here. We have a gradual ramping up of the velocity, and then halfway through the simulation, the velocity is ramped back down again. Another thing we can check to see if there's any problems perhaps with volumetric locking in the elements is to check the pressure. Now, with very, very large deformation, typically we would see this in quadratic elements, where we end up with artificially high stiffness in the element. With linear elements, this shouldn't be so much of a problem. If we were using quadratic elements, then we could check this by checking the contour of pressure, so choosing the stress as the primary variable, and then choosing pressure, and changing from a banded contour plot to a quilt. And if we were to notice checkerboarding, so very large changes in the pressure between elements, then it's possible that we are seeing some volumetric locking in the element. However, here the shape of the pressure contour looks pretty reasonable, and since we also have some frictional contact here as well, this probably is okay. However, it's important to check the pressure profile with the quilt contour option, just to check that you're not getting any problems associated with this volumetric locking phenomenon. So this analysis actually is based off an experiment for which there is experimental data, and according to the analysis, the true in-plane strain in the x direction actually was about 90% strain, whereas we're seeing about 100%. So we're not totally far off. However, there are perhaps some ways in which we could improve the analysis to get closer results, such as changing to quadratic elements perhaps. However, it's quite difficult to match the exact same result as the experiment, since the 12 millimeter displacement that we applied in this case, in the experiment, the plate cracked at 12 millimeters. So obviously we're not simulating the cracking here, and at 12 millimeters, the level of plasticity and the plastic collapse that would be taking place at this point makes it very difficult to achieve an accurate solution for this amount of displacement using nonlinear elastic properties alone. So this is not so bad. I think if we were to repeat the simulation for a lower displacement, we would probably see a much better agreement between the simulation and the experiment. So that concludes the tutorial on how to analyze quasi-static problems with Abaqus Explicit. I hope you found the video helpful. If you have any questions, then feel free to ask. Thanks.